Alright, so here is the notes for 7.6, the natural base e. We're going to use the number e to write and graph exponential functions. Actually, the graphing you can just do on the calculator, so I'm not going to worry too much about that. To represent real-world situations. We also want to solve equations and problems involving e or natural logarithms. Okay, so let's look at something here. Previously, or you should have been exposed at some point to something called the compound interest formula. The compound interest formula stated that if you have, to get a certain amount, you take it's equal to the principal times 1 plus r over n over raised to the n times t power. N is the number of times you compound. R is the interest rate, and t is like time in years. For example, if I did 5,000 compounded monthly for 5 years at, say, 4% interest rate, then plugging those numbers in, I could easily get 1 plus 0.04. Notice I changed the 4% to a decimal. 12, and then 12 times 5. Notice again here, it's the number of compounds. Compounded monthly is the 12. 12 times 5 is, because it's 5 years, and just plug it into the calculator, and you get $6,104.98. It's just a very simple formula, but the reason I bring that up is because if you were to look at that, as you see more compounds, like let's say we went to compound daily or weekly, we would see there would be a slight increase in how much money we get. So the more compounds you can do, the more interest you can gain. Well, because of that, what happens that work? How can I show continuous compound? Well, you can actually show it through a special number called the natural number, which is represented by a lowercase e. So we use e, which is equivalent to approximately 2.71828818, as what is called the natural number. It's very similar to pi. So kind of keep in mind, pi is like an irrational number that we use for circles that can go on forever and ever and ever without repeating. E is the same way. It's just 2.71 instead of 3.14. Okay. So, and our continuous compound formula is slightly different. It is actually A is equal to P times E raised to the RT power. Again, rate and time there. Now, let's look at let's do one quick example here. Let's invest $5,000, same $5,000, but this time we're going to compound it continuously for 5 years at the 4%. So when you do that, again, all you're doing is plugging it in, and you're saying 5,000 times E raised to the 5 times 0.04 power. Plug that into the calculator and you get $6,107.01. Okay, so you should see there that's a little bit more than the other one. So the more increases, the more, and the longer period that you can do this, obviously, the way more you can gain, because eventually this becomes a much bigger deal. So just kind of keep that in mind. Now let's look at some of these properties. The log base e is also called the natural logarithm, and we don't actually write it in log base e. We actually use ln, and that's it. So like the way we say log without a base is log base 10. When you see ln, you're saying log base e. So for example, ln of 3 is the same thing as log e base 3, and you can type that into the calculator. You should find it probably above a button that might be e to the x power, and when you do that, you should get approximately 1.10. Okay, let's look at doing some of those properties like we've done before. How about we switch from logs to, or no, from exponential to logs. Oh, I'm sorry, express in exponential form. So we're actually going from natural logs to exponents. Okay, so ln 4 is equal to 1.39. Then that means I'm saying e to the 1.39 power is approximately equal to 4. ln of x squared is equal to 8. I'm saying e to the 8th is equal to x squared. Keep in mind again, these numbers here are supposed to be the exponents of the base. Let's go the other way. Let's express in logarithmic form. So to express in logarithmic form, again, we're just saying we have it in exponential form. E to the negative 2 is equal to approximately 0.14. That means ln of 0.14 is equal to negative 2. Notice there, I don't have to put the e because the ln is saying log base e. It's symbolic. E to the 2 is equal to 7.39. Natural log of 7.39 is approximately equal to 2. Now notice again, I'm saying that. I'm not saying ln of 7.39. I'm saying natural log. Don't ask me why they do ln instead of nl. They like to say natural log is ln. Go figure. Okie dokie. And let's simplify some things. Let's make sure you understand something. ln, and I actually went ahead of myself there, ln of e raised to the negative 2t power. Keep in mind, ln is log base e, so they would cancel each other out, the ln and the e, leaving you just the exponent of negative 2t. If you said e to the raised to the ln, or to the power of ln parentheses t minus 1, then the ln and the exponent and the e would cancel each other out, leaving you just what it was the ln of, t minus 1. Here's another one, e to the 5 ln x. Now keep in mind on this one, you need the ln and the e next to each other. They want to be close together before they can cancel out. So you have to get them close together. So how could I move that 5? Well, again, the 5 is in front of the ln. So just like on properties of logs, I can move that to be the exponent of the x. Da-da-dum. Alright, so now that they're close together, they can cancel each other out, and then you're left with x to the 5th power. So kind of keep those in mind because you'll probably use some of those properties. Alright, so we have a Halflife formula that we need to look at that involves the E. If you've heard of Half-Life, probably in studying sciences, you know that there's some elements have like these half-lives, how long it takes for certain things to deteriorate. And this would be good for an archaeologist or something like that. The formula there is n of t, which is the amount remaining, is equal to n of 0, which is the initial amount, e raised to the negative k times t power. K is the decay constant, so that is something you would have to find first before usually you can actually answer the problem. So, look at example number 4. It's on page 533. Example number 4 talks about a paleontologist uncovers a fossil of a saber-toothed cat in Bexar County. He analyzes the fossil and finds that the specimen contains 15% of its original carbon-14. Carbon-14 is a thing that they use to measure out the length of something's life. Carbon-14 has a half-life of 5,730 years. Use carbon-14 dating to determine the age of the fossil. Okay, so before we can do that, we need to actually find the decay constant. So what I'm doing here is I'm taking this formula, the half-life formula, and I'm putting in 1/2 equals 1 e to the negative k times 5,730 power. You would have to do this first, okay? Before you're actually even solving the problem, you need to do this first. So this right here, that 1/2 and that 1 will always be part of the first step, first problem, right? Be on a test, this might be a separate question. Find the decay constant, because you need to find that k first. So you do that. Divide by 1 is nothing, so you really still have 1/2 e to the k whatever power. And since we're going to try to get rid of the e, we're going to do natural logs. So notice here my next step is just taking the natural log. Okay, if I take the natural log of 1/2, remember the e's cancel each other out, leaving me the negative 5,730k. The natural log of 1/2 is negative 0.6934. In reality, this will always be true. This right here, these first steps should always be right there. So the only thing that might be different is whatever number is your half-life. And so if you take this number and divide it by the half-life, you should always get your k. Okay, so keep that in mind. So go ahead and figure that out, and when you divide, you would get 0.000121. Okay. Now I actually went a little further because my calculator showed me more, so I might have a slightly different answer than the book because of that. Because I think because I gave it a little extra numbers, but that's okay. I'm just a little bit more accurate. Okay, so now we're back to the original problem. Now we put the number in for k, and notice I'm looking for t, because the original question was, how old is this thing? How long has it been? Okay, so if only 15% is left out of 100%, notice how I'm writing that, 15 and 100. The initial amount is the 100, 15 is what's left. Okay, from there, I would divide out the 100. 15 divided by 100 is 0.15. And I'm going to take the natural log of those, so that way I can get rid of the e. The natural log of 15 is equal to negative 1.89712, and again I'm going to divide by the negative 0.00121. When I do that, I get 15,679 years. Like I said, that is a little bit different than what they got in the book, but that's mainly probably because of the way I typed it into the calculators, and I was just always using answers. So actually mine should be a little bit more accurate because there's not as much round off error. I think we might spend an extra day on this to say work on this, so we might delay the test even another day to give you some more practice problems with it, but you do expect that you need to work on this in class because it is going to be very important to try to get a concept of this. This test could have quite a few word problems that should be done in class. So keep that in mind and make sure you're preparing yourself with your note card. That is it for today, and we will work on this tomorrow.